Okay, this is section 5.5, systems of nonlinear equations. So basically we're going to extend the ability to solve systems of equations to include systems that have equations that are nonlinear. So here are the key concepts, or the key definitions. So a system of nonlinear equations in the variables x and y, as we're going to stick with, is a set of two or more equations such that at least one of the equations has a variable, either x, y, or both, raised to a power other than 1. So in our case, we're going to stick with systems of two equations, and the greatest power that any of our variables will be raised in the original system will be 2. So a solution set, just like a solution set to any system, is a set of ordered pairs, and in this case there will usually be more than one, that make both equations true. So I'll have a solution as an ordered pair x and y. Our original equation system has two variables. When I plug in the value of x and I plug in the value of y, both equations have to be true. And here is two extra things. The solutions to these systems can be real numbers or complex numbers with non-zero imaginary part. And here's the other kind of unfortunate thing, although I'll give you all a break on the exams depending on what I put on there. Since it's nonlinear, we have to check each proposed solution in the original system to see if it works. So there's that extra added step at the very end of checking. So let's look at this particular example. I think there's only 4 examples here, and that's as deep as we're going to go. I actually put an applied, the very last example in the book. There is an applied problem. It turns out to be a degree 4 polynomial, and I deleted it because we've not gone over how to solve those. So we're not even dealing with it. So we always have the substitution method. So here's some things to take note of. So one equation, equation 1, is quadratic, or we'll say a degree 2 equation. So we could actually rewrite equation 1 as x squared minus 4 is equal to y, or x squared minus 4 is equal to f of x, with the replacement of y is equal to f of x. And you should know now how to easily sketch that particular equation, or the particular graph of that equation. I'm going to say right here is going to be the point 0 and minus 4. And it's going to be a parabola, right? It's going to be a parabola that opens up. So on the other hand, give me some more room here now that I have the information down. On the other hand, equation 2 is linear. Indeed, it's y is equal to minus x minus 2. So minus 0 minus 2 is going to be its intercept. The slope m is minus 1. So it's going to look something kind of like this. So we expect, just by the graph here, we expect an intercept at 2 points. Now, it may not be the 2 points I've graphed, but we expect, by the graph, we expect 2 solutions. So in this particular case, we can use, if I have a degree 2 equation and a linear equation. Anytime one of your equations is linear, and I'll write this down, if one equation is linear, and by linear, remember, that means it's a degree 1 polynomial in the variables x, y. That means there's no exponent other than 1 on the variables. Use the substitution method. And it doesn't really matter which method we use, but if I look at equation 2 and I solve for y, I get y is equal to minus x minus 2, which is equal to minus x plus 2. Now, as it turns out, you may not like that minus sign. If you don't, then solve for x instead of y. Then you'll get x is equal to minus y minus 2. So there's not going to be anything we can really do. But that's going to be okay. It's going to be okay. So now that I've solved for y, let's go back to my equation 1. And let's replace my value of y that I find here for x. So I get x squared. Yeah, for this one, you don't want to solve for x. You always want to solve for the nonlinear. That's the negation. You want to solve for the variable with exponent 1 in both equations when that's the case. So in that case, it's the variable y. So I've done that now, and I've found that y is equal to minus x plus 2. So I'm going up to equation 1, I'm going to replace y with minus x plus 2. So it's x squared minus, that's there. And then I have to bring along what y is, and it has its own minus. And that's equal to 4. So that's the same as x squared minus a minus is plus x plus 2 is equal to 4. And the way to solve this is to take it into quadratic form. X squared plus x, bring the 4 over and it becomes minus. So that gives me minus 2 is equal to 0. So think about factoring. This is something that's easy to factor. If you can't factor, you have to use the quadratic formula. So here, x plus 2 times x minus 1 is the factorization. So that implies x plus 2 is equal to 0, which means x is equal to minus 2, or x minus 1 is equal to 0, which implies x is equal to 1. So here are my two x values. So I have two x values. So as always, we're going to write these as ordered pairs. So my solution set is going to have two ordered pairs in it at most. And one of them is going to have a value of x is equal to minus 2. And the other will have a value of x is equal to 1. Now, I may have to erase one of these solutions, but let's check and see. So let's go back and choose any of the equations, and let's solve for the other variable. And clearly here, the easiest one to use is the fact that y is equal to minus x plus 2. So let's come down here and let's note that y is equal to minus x plus 2. So y is equal to minus 2 plus 2. So that's y is equal to minus 0, which is 0. Over here, again, y is equal to minus x plus 2. Y is equal to minus 1 plus 2. So that's y is equal to minus 3. So here's my two possible solutions. So let's go back and let's check both of them. Here's my original set of equations. Here's my proposed solution set. Minus 2 and 0 and 1 and minus 3. So if I plug in minus 2 in the first and 0, so I'm going to plug in minus 2 is equal to x and 0 is equal to y. And clearly that makes the first equation true because minus 2 squared is equal to 4, 4 minus 0 is equal to 4. If I plug in minus 2 for x down here and 0 for y in the second equation, then I get minus 2 is equal to 2. So clearly that is a solution. Now let's go up here and plug in 1 and minus 3. So 1 squared minus a minus 3 is 1 plus 3, that's equal to 4. So it checks out 1. What about 2? 1 plus a minus 3 is minus 2. So both of those work. So my solution set is the two ordered pairs, minus 2 and 0, and 1 and minus 3. So my sketch of the graph was off as to where the actual points occurred, but in the end, I did have indeed 2 points. We can actually check that out. If we go to Geogebra, it might be helpful for you to see this. And one of the equations was x squared minus 4. And the other equation was y is equal to minus x minus 2. And right there we have our two solutions. Minus 2 and 0. And 1 and minus 3. So that's the visual exploration of a parabola that is intersected in two places by a line. Well, it leads us to wish to explore that figure a little bit more. So right here are the three possibilities. So this is when one equation is quadratic in the variable x. So you have x squared plus y. Y is a degree 1, and x squared has degree 2. So either we have no intersections, one point of intersection exactly, which would be right there, or we have two intersections, and that's it for that particular type of a system. So it's either 0 points, 1 point, or 2 points. It's impossible for a line to intersect a parabola at an infinite number of points. It just can't happen. So it's either none, no solution, one solution, or two solutions, and that's it. And I have concentrated on those types of problems for your homework. I didn't give you that many homework problems. So let's look at another example. So really, this example is quite a bit different, right? We have both variables are degree 2 variables. So our system is given by equation 1 is x squared plus y squared is equal to 4, and 2x squared minus y squared is equal to 8. So I'm going to again deviate a little bit from the way the book does this, because I'm trying to get you into matrices. So here we have an x squared term, a y squared, because the only thing that really matters is the coefficients. You have to know what the variables, the coefficients belong to, and that's the reason I put those up here. And this is going to be my equal sign. So my variable in my first row is 1 and 1 and 4. And here I have 2 and minus 1 and 8. So that leads to the following matrix: 1, 1, 2, minus 1, and 4 and 8. So what we want to do here is I want to do my new, so remember this is my row 1 and my row 2. So my new row 2 is going to just be row 1 plus row 2. So let me get some more space up here. So this is my new row 2. So my row 1 does not change at all. So my new row 2 comes about by adding row 1 and row 2. So row 1 and row 2, 1 plus 2 is 3. 1 plus minus 1 is 0. And 4 plus 8 is 12. So now let's remind ourselves what our variables are. So row 2 tells me that 3x squared plus 0 y squared is equal to 12. So literally I get 3x squared is equal to 12. So let's divide both sides by 3. And that's going to give me x squared. 12 divided by 3 is 4. And now let's use the principle of square root. That means x is equal to plus or minus the square root of 4, which implies x is equal to 2 or minus 2. So that means we have a possible set of solutions, 2 of them to be specific, in which in one case x is equal to 2, in the other case x is equal to minus 2. So I have to find the corresponding y values. But in this case, we'll go back up and we can grab any one of the equations and solve. So I'm going to grab equation 1. So equation 1 says x squared plus y squared is equal to 4. So I have the value of my x here, so let's plug it in. I'm going to do one little thing just to ease things. I'm going to solve for y. Y squared is equal to 4 minus x squared. So y squared is equal to 4 minus, and my x value here is 2. So that gives me y squared is 4 minus 4. So y squared is equal to 0, means y is equal to 0. Let's do it one other time. Y squared is equal to 4 minus x squared. And now my x is going to be minus 2. But minus 2 squared is still 4. So y squared is equal to 0 over here. So my two possible solutions are minus 2 and 0 and 2 and 0. So with that information, where are we at? Yep, right, here we are. Let's go up and let's check it out. So my two possible solutions are -2 and 0 and 2 and 0. I meant to write that in another color, but that's okay. So let's plug in -2. Well, I already know it satisfies the first equation because I used the first equation to find my value of 0. So all I have to do is check in my second equation. So 2 times -2 squared minus 0 squared is equal to 2 times 4, which is equal to 8. So that one checks out. Now let's check out my other one. 2, when x is equal to 2, times 2 squared minus 0 is equal to 2 times 4, which is equal to 8. So that also checks out. So that is my solution set right there. 0 minus, minus 2 comma 0 and 2 comma 0. So those are my 2 points of intersection. So you can imagine what that looks like. As a matter of fact, let's take a look and see what that looks like, just so you can get a visual. So my first equation was x squared plus y squared is equal to 4. You should recognize that as a circle. Circle of radius 2, right there. And my second is a little bit different. You don't know what this one's going to be because it's not quite a circle. It's called a hyperbola. So as you can see, we have, this is an odd, probably the graph of this second equation, since it has a minus in it, it's hyperbolic. You've probably not seen one of those before, but you can see right there the intersection is just 2 points at -2 and 0 and 2 and 0. So you need to do this algebraically. You can't just, pull up, if you see this on the exam, just pull up Geogebra and find the answers. You need to derive the answers algebraically. Okay. So example 3. Example 3 is an odd one. But we're going to do the same thing. We have two equations. And I'm just going to go ahead and just write out the matrix. We have x squared, xy, y squared, and then my equals. Little in just 2 rows. So my first coefficient for my x squared term in my row 1 is, I can get it back to, there we go, a 1 and a 3 and a 1 and a 22. Down here I have a 1 and a minus 1 and a 1 and 6. So that leads to the following matrix. It's called an augmented matrix, 1, 3, and 1. Then the line is 22. Just remember what these numbers are as they relate to the equations. Then I have them 1, minus 1, 1, and 6. So what I'm going to do is I'm going to say my new row 2 is equal to row 1 plus my old row 2. So that's going to give me the following. So this is my new row 2. That's the only thing that's going to change. So just go ahead and we repeat our row 1 up here. And I'm just adding row 1 and row 2. So 1, actually it looks like I need to add minus row 1 plus row 2. Yeah. So minus 1 times 1 plus 1. So let me write this again, maybe a little bit better. What I need to do is I need to multiply row 1 by negative. That's what I want to do. I want to get rid of some of these coefficients. So it's minus row 1 plus row 2. So minus 1 times 1 plus 1 is 0. Minus 1 times 3 is minus 3. Minus 1 is minus 4. And minus 1 times 1 plus 1 is 0. And minus 22 plus 6 is minus 16. So what does that give us? That gives us, let's remember this corresponds to x squared, xy, y squared, and y equals. This tells me that minus 4xy is equal to minus 16. I'm going to get rid of those minuses by multiplying both sides by minus 1. Actually, I could do another operation on the matrix. New. My new R2 is equal to minus R2. And then that would take away. But I don't have to do that. I can just do it over here. I'm going to multiply both sides by minus. So I get 4xy is equal to 16. Now I'm going to divide both sides by 16, which would correspond to another operation. My next newest R2 would be 1/4 times R2. So which is I'm just dividing both sides by 4. And you don't have to do this over here. I'm just telling you that operations over here with the variables in place actually correspond to matrix operations I could use if I wanted to. Anyway, this gives me x times y is equal to 4. Now what I'm going to do is I'm going to solve for y. Now I could solve for x, but I've decided I'm going to solve for y. You've got to make a decision, and I decided solve for y. So y is equal to 4 divided by x. And here is my big complaint with the textbook. Provided x is not equal to 0. We don't know what the value of x is, people. X is still an unknown. So if x happens to be 0, this won't work. And the book does not say that. And I have shown again and again in classes, not in a lecture here, but in class when I look at student solutions, why certain moves don't work. But right here, I'm just going to keep this in mind. And we're going to say provided x is not equal to 0. So we're assuming x is not equal to 0. Now, at the end, we need to go back and then assume x is equal to 0 and see what we get. And we probably will get no solution. Now, we're not going to do any of that. But that's the true mathematical way that we would have to do it. So we're going to say y is equal to 4 over x. So I'm going to come back up to my original equations. I need to see them here. And I think it's going to be easiest to look at equation 2. So equation 2 says that x squared minus xy plus y squared is equal to 6. So remember, I have this little thing that y is equal to 4 divided by x, provided x is not equal to 0. So I'm going to go ahead and use that information. That implies x squared minus x, y is 4 divided by x, plus 4 divided by x squared, so I'm just replacing y with 4 divided by x, is equal to 6. So simplify x squared minus the x's cancel, so I get minus 4 plus 16 over x squared is equal to 6. And here we have a situation. I have an x squared in the bottom. Of course, I'm assuming x is not equal to 0, so I have to clear that denominator by multiplying both sides by x squared. That's going to give me x to the 4th minus 4x plus, 4x squared plus 16 is equal to 16x squared. So it's going to be something we can solve, but we're going to have to use a trick. Let's put it in everything equal to 0. So that's going to give me x to the 4th minus 4x squared minus 16x squared plus 16 is equal to 0. Wait, did I do something wrong here? I did. I suddenly made that 6x squared into 16x squared. There, it's fixed. And simplify. So here's what, this is a degree 4 equation, but let's make the substitution. We've done this in the past. Let w, or whatever variable you like, not x or y, let w equal x squared. That means w squared is equal to x to the 4th. And we're going to rewrite this. So x to the 4th is w squared. X squared is equal to w. So now I have a quadratic in the variable w, and I can factor this. This is going to factor to w minus 2 times w minus 8 is going to be equal to 0. So that's going to imply directly, I don't think I should have to do anything here, that w is equal to 2 or w is equal to 8. But recall, my original's not in terms of w. I have to go back and substitute in my value of x for w. So that implies x squared is equal to 2, which in turn implies x is equal to 2 values plus or minus the square root of 2. This is going to imply that x squared is equal to 8, which implies that x is equal to plus or minus the square root of 8. But since 8 is equal to 2 squared times 2, that's the same as 2 Let me write my plus or minus in there. That's plus or minus 2 on the square root of 2. So look what I have here now. I have 4 possible solutions. One is the square root of 2. I don't know the y value. The other is minus the square root of 2. I don't know the y value. The other is 2 on the square root of 2. I don't know the y value. The other is minus 2 on the square root of 2. I don't know the y value. So I have to find the y value here for all of these possibilities. Well, how do I find the y value? I go right back up here. I'll just rewrite what I had. Just is it going to work? Not so bad. Good. That's not so bad. So if you recall what I just showed you up here, we have that y is equal to 4 divided by x. So that means I have to use all of these values of x to find out what y is. So y is equal to 4 divided by the square root of 2. Now in math we rationalize the denominators. I know we're not emphasizing that ability so much in intermediate algebra, but you multiply by the denominator here, the square root of 2, over the square root of 2, so that gives me 4 on the square root of 2. The square root of 2 times the square root of 2 is just 2. So that gives me 2 on the square root of 2. So I'm going to get, if I instead use minus the square root of 2, I'm going to get minus 2 the square root of 2. The only thing that's going to change is the sign. So now let's use y is equal to 4. Notice that x is not equal to 0 in any of these cases, so we don't have to worry about it. 4 divided by 2 on the square root of 2. Well, that simplifies to 2 on the square root of 2. And when I rationalize the denominator by multiplying by 1, disguised as the square root of 2 on the square root of 2, I get 2 on the square root of 2. Square root of 2 times the square root of 2 is 2. The 2's cancel. I get the square root of 2. And then I'm going to get minus the square root of 2 for the last. And I'm not going to bother to check, but it would be interesting to see what this looks like. So let's see what kind of graph this actually looks like. So go to Geogebra, and let's input the original equations. So I had x squared, equation 1, plus 3 times x times y, plus y squared. I'm assuming it will do this. Is equal to 22. Wow, look at that. That's another type of hyperbola that's we move out. It's kind of like what we just saw before, except it's slanted on the side. And here we have x squared minus x times y plus y squared, and that's going to be equal to 6. Cool. So we see we have 1, 2, 3, and 4 solutions. Now, I don't know if you realize, but the square root of 2 is approximately 1.414, blah, blah, blah. So right there, the square root of 2 and minus the square root of 2 appear. And clearly, if you multiply minus 1.41 times 2, you get 2 times the square root of 2. And you see that we got the right answer. And, you know, of course, I know there's no way you could, this is an ellipse, and this is a hyperbolic surface of some sort, so, or hyperbola of some sort. There's no way you could get that by graphing, but we could get the solution by algebraic means. Again, I'm going to concentrate more on the problems of the first and the second type. And the reason I'm bothering to do these last problems, example, what was that, 3? I completely skip example 4 in the book, which has to do with the absolute value. So let's not belabor this. And the absolute value doesn't focus on what I want to focus on here. So let's do this one last one. And again, the focus is going to be the intersection of, say, a parabola with a line, or maybe a circle with a line. Something that makes it a lot easier. So here we have our system. And again, I'm going to go ahead and translate this into a matrix. And you don't even have to do this step. You could go immediately to the matrix. But I'm going to have an x squared value and a y squared value, and it equals. So my first row, the coefficient on my x is 1, x squared is 1. The coefficient on my y squared is 1, and my equals is 5. Coefficient on my second row, on my x squared term, is 4. 3 on my y squared term, and 11. So that gives the following matrix: 1, 1, 4, and 3. These are called augmented matrices. 5 and 11. So what I want to do, again, I always want to get a 0 right here in my entry. So the diagonal and then a 0. So I'm going to say my new row 2 is going to be equal to minus 4 times my row 1 plus my existing row 2. So the only thing that's changing is going to be my row 2. So this gives me, we'll go ahead and just write out exactly what our row 1 is. No change there. So minus 4 plus 4 is 0. Minus 4 times 1 is minus 4, plus 3 is minus 1. Minus 4 times 5 is minus 20, plus 11 is minus 9. Now I'm going to go ahead and do one more thing. My new row 2 is going to be minus my existing row 2. Just so you can see all of this. So that's 1, 1, 5, 0. I'm just multiplying row 2 by negative 1, 1, and 9. So now let's go back. This tells me that 0, concentrating on my row 2, x squared plus 1 y squared is equal to 9. In other words, y squared is equal to 9. Which means y is equal to plus or minus the square root of 9. So y is equal to plus or minus 3. So in my solution set here, I don't know what the x is, but the y value in one instance is 3, and we're not going to check these, it's just too much. You're supposed to check, and if you were doing these you would. But on the exam, if they're complicated, I will tell you to check your answer, let's put it that way. So y is equal to 3 or minus 3. So let's go back and grab an easy equation. From my original equation, I have x squared plus y squared is equal to 5. So you want to use the other. Since I reduced row 1, I want to use row 2. Sorry, I said that exactly wrong. Since I did row operations to get rid of the coefficients on the row 2, I want to go back to row 1. So row 1 says x squared plus y squared is equal to 5. I'm going to be solving for x. X squared is equal to 5 minus y squared. So since y is the negative, my values of y are just negatives of each other, all I have to do is do this once, because y squared, 3 squared is the same as minus 3 squared. So x squared is equal to 5 minus 3 squared. So that gives me x squared is equal to 5 minus 9. So x squared is equal to minus 4. So that implies x is equal to plus or minus the square root of minus 4. That means x is equal to plus or minus 2 times the square root of minus 1. That means x is equal to plus or minus 2. And what is the square root of 1? By definition, I. So I will put 2i here and minus 2i here. I'm going to have more than that, so think about it. I have 2 solutions for x and 2 solutions for y. So I'm going to have a total of 4 solutions. So 2i and minus 3, and then minus 2i and 3. Interesting question for you. Can we plot this? Can this be plotted to check? And the answer is a resounding no, because you have no idea what or how to plot anything that has a factor of the imaginary unit I. Now, our class can't. We could plot this in another class. But for now, that's it. Concentrate on what I give you in the homework and on the first 2 examples.